Well, we are going to learn about a new type of multiple comparisons test, which is called Tukey's method. Tukey's honest significant difference. Honest significant difference. So in this technique, we have the following setup. The setup is this: we have some y1 to some yk, they are independent, and yi follows normal mu I sigma squared. We have some random variables y1 to yk independent following these distributions, and we have some sigma square hat which has the following property, which is of the form sigma square divided by p chi-square p. So by this I mean that there is a thing called sigma square hat which has this distribution. It has a chi-square p distribution divided by p and multiplied by sigma square. And this quantity is independent of your yi's. So this is the setup, which might look like a pretty complicated setup, but we will see that in a linear model situation, this setup is readily available. If you have this setup and you are interested in testing H naught ij, which is mu I equal to mu j for all I not equal to j, that is your multiple hypothesis setup, then Tukey's honest significant difference method is one way of accepting or rejecting each one of these k choose too many null hypotheses. Of course, the alternative hypotheses are that they are not equal. Now the technique is the following. So this is the test. What you do is you compute the studentized range. So the studentized range is you compute the range of these things. The range of these things is maximum of the yi's minus minimum of the yi's. That's the range. Studentize it, that is divided by sigma hat, which is square root of sigma square hat. So you divide this by this quantity. This is generally denoted by the letter Q. So that's your test statistic. You are going to test based on that. And how are you going to assign, accept or reject to each of these hypotheses? The technique is based on the fact that if all the H naught ij's are true, then the distribution of Q is completely known. It does not depend on sigma square or the mu's. So here's a fact. If H naught ij's are all true, then Q has a known distribution. By known distribution, I mean something that does not depend on the unknown sigma square and the unknown common value of mu i's. If all the H naught ij's are true, then all the mu i's are same. I do not know what that common value is, but the distribution will not depend on the common value. And you can sort of easily see that, because if I add the same constant to all of them, that will effectively change the common value. Because I am subtracting mean from max, so the entire thing will remain invariant under the thing. If I multiply everything with a constant number, then this and this will both get multiplied by the same number, so it will just cancel each other out. But the distribution is not something that we already know from our everyday experience or one of those standard distributions, but this is completely known and this has been worked out and tabulated and all its quantiles etc. have been tabulated. So this is Tukey's Q distribution. So once you have that Tukey's Q distribution, then I will perform the multiple hypothesis testing using the following test statistic. So what I will do is, you will accept, or write it in form of reject H naught Ij if and only if yi minus yj divided by sigma hat, which is square root of sigma square hat, exceeds if this exceeds q1 minus alpha. Incidentally, this Q distribution will of course depend on the K. I am not writing that K, so it depends on K. So Q1 minus alpha is the 1 minus alphath quantile. So if you are using alpha to 0.05, then it is the 95% thing. So if it is the distribution, it is this value, this is Q1 minus alpha, such that this area is alpha. So if this happens, then you say reject. Now I claim that this will keep the family-wise error rate less than or equal to alpha. And why is that? That's pretty straightforward. So if WER is less than or equal to alpha in this case, and the reason is the simple. What is FWER? The chance that you will reject at least one H naught Ij when all the H naught Ij's are actually true. Now, if you reject at least one of them, this means that this difference exceeds this value. If this difference exceeds this value, definitely this must exceed that, because this is the maximum difference of all the Yi's and Yj's. So if sum yi minus yj by sigma hat exceeds q1 minus alpha, then definitely q exceeds q1 minus alpha. And the chance of that happening is already alpha. Therefore, if this happens, then that must happen. So, at least one H naught Ij is rejected is a subset of this event. And this event has probability alpha. So, the probability that at least one of the things gets rejected has probability less than or equal to alpha. And that shows that family-wise error rate is less than or equal to alpha. So, that is one test.